In physics, we explore the very small to the very large. The very small is a small fraction of a proton, and the very large is the universe itself. They span 45 orders of magnitude. A 1 with 45 zeros. To express measurements quantitatively, we have to introduce units. And we introduce, for the unit of length, the meter, for the unit of time, the second, and for the unit of mass, the kilogram. And you can read in your book how these are defined and how the definition evolved historically. Now, there are many derived units which we use in our daily life for convenience, and some are tailored towards specific fields. We have centimeters, we have millimeters, kilometers, we have inches, feet, miles. Astronomers even use the astronomical unit, which is the mean distance between the Earth and the Sun, and they use light years, which is the distance that light travels in 1 year. We have milliseconds, we have microseconds, we have days, weeks, hours, centuries, months, all derived units. For the mass, we have milligrams, we have pounds, we have metric tons. So lots of derived units exist. Not all of them are very easy to work with. I find it extremely difficult to work with inches and feet. It's an extremely uncivilized system. I don't mean to insult you, but think about it. 12 inches in a foot, 3 feet in a yard, that drives you nuts. I work almost exclusively decimal, and I hope you will do the same during this course, but we may make some exceptions. I will now first show you a movie which is called The Powers of 10. It covers 40 orders of magnitude. It was originally conceived by a Dutchman named Kees Boeke in the early 50s. This is the second generation movie, and you will hear the voice of Professor Morrison, who is a professor at MIT. The powers of 10, 40 orders of magnitude. There we go. I already introduced, as you see, their length, time, and mass, and we call these the 3 fundamental quantities in physics. I will give this the symbol capital L for length, capital T for time, and capital M for mass. All other quantities in physics can be derived from these fundamental quantities. I give you an example. I put a bracket around here. I say speed, and that means the dimensions of speed. The dimensions of speed is the dimension of length divided by the dimension of time. So I can write for that bracket L divided by bracket time. Whether it's meters per second or inches per year, that's not what matters. It has the dimension length per time. Volume would have the dimension of length to the power of 3. Density would have the dimension of mass per unit volume, so that means length to the power of 3. All important in our course is acceleration. We will deal a lot with acceleration. Acceleration, as you will see, is length per time squared. The unit is meters per second squared. So you get length divided by time squared. So all other quantities can be derived from these 3 fundamentals. So now that we have agreed on the units, we have the meter, the second, and the kilogram, we can start making measurements. Now, all important in making measurements, which is always ignored in every college book, is the uncertainty in your measurement. Any measurement that you make without any knowledge of the uncertainty is meaningless. I will repeat this. I want you to hear it tonight at 3 o'clock when you wake up. Any measurement that you make without a knowledge of its uncertainty is completely meaningless. My grandmother used to tell me that, at least she believed it, that someone who is lying in bed is longer than someone who stands up. And in honor of my grandmother, I'm going to bring this today to a test. I have here a setup where I can measure a person standing up and a person lying down. Not the greatest bed, but lying down. I have to convince you about the uncertainty in my measurements, because a measurement without knowledge of the uncertainty is meaningless. And therefore what I will do is the following. I have here an aluminum bar, and I make the reasonable, plausible assumption that when this aluminum bar is sleeping, when it is horizontal, that it is not longer than when it is standing up. If you accept that, we can compare the length of this aluminum bar with this setup and with this setup. At least we have some kind of calibration to start with. I will measure it. You have to trust me. During these 3 months, we have to trust each other. So, I measure here 149.9 centimeters. However, I would think that so this is the aluminum bar. This is in vertical position, 149.9. But I would think that the uncertainty of my measurement is probably 1 millimeter. I can't really guarantee you that I did it accurately any better. So that's the vertical one. Now we're going to measure the bar horizontally, for which we have a setup here. Ooh, the scale is on your side. So now I measure the length of this bar. 150.0 horizontally. 150.0, again, plus or minus 0.1 centimeter. So you would agree with me that I am capable of measuring plus or minus 1 millimeter. That's the uncertainty of my measurement. Now, if the difference in length between lying down and standing up, if that were 1 foot, we would all know it, wouldn't we? You get out of bed in the morning, you lie down, you get up and you go clunk, and you're 1 foot shorter. And we know that that's not the case. If the difference were only 1 millimeter, I'm nervous because I hope that physics works. So I take my calculator,